My dear Robert, the floor is yours.
Thank you very much for the kind introduction. Welcome everyone after lunch. I hope you had a good meal and you already got a cup coffee, that you're not too sleepy. I try my best to avoid this from my side. I'm very happy to give this talk here on confidence properties. It's a new way to look at Monte Carlo, the Monte Carlo error, and there are many open questions related to that topic, especially when it comes to the hyperbolic cross. So I hope that many people get then finally interested in that. It's joint work with Daniel Rudolf, who is unfortunately not here on this workshop, but some of you know him. At this point, I wish to greet Daniel Rudolf asked me to greet everyone who is here in the audience and knows him. So then, let's start. It's much about this talk about the error criterion for Monte Carlo. So the basic problem is we want to compute an integral of a divariate function. Well, the function is from some class of integrable functions, and we want to use randomized methods. Omega, this is it should be from a probability space, and the small omega is the sequence of random numbers we are using for that particular realization of the algorithm. So the algorithm of maps, it uses n function values at random points and uses these function values to approximate the integral. Usually, the error is defined in terms of the standard Monte Carlo error, which is the root mean square error. Write it like the error of Monte Carlo 2 mean, the second mean, quadratic mean. So we take the supremum of all functions from that input class and ask for the root mean square error that algorithm has for approximating that integral of that function. This criterion is especially nice because in some cases, for example, if you have given the L2 norm of f and you have standard Monte Carlo method, and you can explicitly give the error of the Monte Carlo method, the standard Monte Carlo method, in terms of this error criterion. But for some analysis purposes, it's simple. It's easier to simply consider the expected error, denoted here by the simple mean Monte Carlo. So that you take the supremum over all inputs and then the expected error for that input. A lot of work has been done with that criterion, but it turned out that there are problems where it's not applicable, that criterion. I have an example. It's from Hickanel and co-authors who considered some cone of functions. Lebesgue functions in that case, we have some ratio on different norms, but no absolute bound on the norm, so it's an unbounded set. It looks a little bit like a cone. And but they have said we can still give an algorithm for that. But the way they said that the algorithm is working was a bit different. They said given any error threshold and any uncertainty level delta, so or confidence level would be 1 minus delta, we can find an algorithm which guarantees that the probability that the algorithm exceeds that threshold epsilon is bounded by delta. And this holds for all functions from that input class. And the idea was exploiting a known bound on the ratio of different norms of the function. We can first estimate the norm of the function, and then after this estimate, for which we use a fixed sample, we can decide how many more samples do we need in order to give an absolute accuracy to bring the error below that threshold epsilon. So it's an adaptive algorithm. The sample size is not fixed, but it does its job. And there's been a joint work together with Daniel Rudolf and Ullrich It was called solvable integration problems. We have studied this problem taking a closer look, considered also other cones, and tried to say something about optimality. But we also find out that the criterion of the expected error is not applicable in that situation. And he said for any adaptive algorithm, where we could vary the sample size depending on the random numbers we take and the function we put in, could all depend, could be adaptive, no matter what. The supremum over all functions from that input set of the expected error could be infinite. This is infinite. Yeah? It's unbounded. There's no limit for this. So it's not the right criterion here to ask for the expected error. In a way, some error with confidence or uncertainty, some probabilistic error criterion will be more general. And it might be also interesting to study this other criterion in a more classical situation, which I want to do in the next, in the following of the talk. Let's take a classical look, the classical setup. The input set should be the unit ball of a function space, so we have some norm bound. And we fix the number of function evaluations, so we have algorithms an, so n indicates how many function evaluations we take. And this will be, but in a way we will have probably different methods will be required to achieve optimality in a different setting. We define the nth minimal probabilistic Monte Carlo error at uncertainty delta. That is this. It's the smallest epsilon for which there still exists an algorithm using n function values such that for all functions which are bounded with respect to the norm of that space, the probability that the algorithm has an error exceeding epsilon is bounded by delta. And analogously, we can define the epsilon delta complexity. So the minimal number of function values required in order to achieve that error, to match that error criterion. So I want to put those quantities in contrast to similar quantities for the expected error. I denote them Monte Carlo mean and error and complexity. Yeah. So let's see how methods need to be changed, altered for this new criterion to have optimality. The first example I want to talk about is classical isotropic Sobolev spaces. You're probably all used to those norms. So we take some multivariate derivative, but the joint degree of the partial derivative should be bounded by the smoothness R. These spaces with that norm bounded are functions which are bounded in that norm. They make up the isotropic Sobolev spaces. And to make it simple, the lower bounds are quite easy to be found. They look like this. I have, depending on the integrability index of that Sobolev space, P, take the minimum of P and 2, define this with Q, and then we have some lower bound where there is some improvement possible, or it's a bit smaller than a deterministic bound with some factor which includes the logarithm of delta and n, and some exponent where this Q pops up. We will have a closer look at this bound when we have a case where this is the optimal bound. Just the idea, how do we prove this? This is usual, an average case setting with smooth bump functions. So for low integrability, we take few bumps. We don't know where they are, but a function which, an algorithm which should be good for such an average case setting, don't know where the bumps are and in which direction they show. And there we get lower bounds from this uncertainty we have in an algorithm. So I only learn something about one bump or one interval. With one function value, I can only learn something about one interval. Yeah. And for high integrability, there are bumps everywhere, but random, and I don't know how they are. So usual proof technique, but we achieved this bound. First, very straightforward method to achieve good confidence properties is some scheme of probability amplification. It's the median trick. So suppose we have a Monte Carlo algorithm for which we have that with probability at most 1/8 we exceed a given threshold epsilon. Then we can construct a new method by taking the median of k repetitions of that algorithm, the independent repetitions, and then the bound, the probability that the new algorithm exceeds epsilon is bounded by something which which decays exponentially on the number of repetitions. This means we have an algorithm when beforehand we used m function values, then we use k times m function values for the new algorithm. So if this should be smaller than some given delta, then k will be logarithmic in 1/delta. This is what actually happens. And the reason why this works is if more than half of those repeated executions of that randomized algorithm have an error smaller than epsilon, then the median will be one of them and will also have that smaller error.
And the order of k and m is also somehow random.
K and m?
You put the order in different.
Here?
No, on the left. AKM and
Is
then
equal
you
to
have
AS.
AMK.
Okay, it should be the same. Okay, sorry. It's good. Someone is reading the slides very carefully. It's a good sign. What I want to put stress on, taking the median is a non-linear feature. So usual Monte Carlo methods which we discussed for integration, they are always linear for the integration problem. But here we have some non-linear feature. And in some cases it's really necessary, in some cases probably non-linearity is not totally required, but we don't know. We have some algorithms which include some non-linearity and have optimal properties. We could apply this to known algorithms for known Monte Carlo algorithms for integrating functions from those Sobolev spaces, and they're known for the whole domain, also for low smoothness. We have this 1 minus 1/q, this is an improvement in the rate. So you can find those results, for example, in Heinrich, where low smoothness was treated. And then we have that the probabilistic Monte Carlo error, depending on n delta, is bounded by this bound, where we have the correct power in n, but the power of logarithm of delta is to the -1. This is a bit too big. We should not expect that this has an additional power r/g, this logarithmic term. And there's another drawback. This holds only for n being bigger than logarithms of 1 minus 1/delta, which is because if we prescribe a certain confidence level, we need a certain amount of repetitions, and so we can't take too few function values. Using this technique, we only have matching lower bounds for the Lebesgue spaces, so functions without smoothness. This is then the correct order. We have the correct order for LP spaces. And the algorithm is the median of means. So you take the standard Monte Carlo method, like sample average of uniformly identical, uniformly distributed and on the domain. And then you repeat this several times, take the median. This is the median of means, and you get this rate. That's only for n being bigger than logarithm of 1/delta. But this is already a good starting point, having this exact rate for the LP spaces, because we can combine this in a very well-known way, which is contra variates or separation of the main part. If we have sufficient smoothness, then we achieve this rate. It matches the lower bound. And we can also write this in terms of the epsilon delta complexity. It looks a bit more complicated, but I will come back to that. And the idea is of this is simple, quite simple. Spend half of the budget on deterministic LQ approximation and half of the budget on the median of means for the LQ residual. And if we take too few samples, then we use purely deterministic methods. So how does this turn out? This rate, n to the minus r over d, this is the deterministic rate, and we can't fall below. If we want to have too much certainty, if delta is too small, then we can simply take the deterministic integration method, and we have 100% certainty. But if we relax a little bit on the confidence level, delta is a bit bigger, then we can include this separation of the main part and have some factor which shows the benefit of Monte Carlo. Or if you look at this here, down here, we either the complexity is either the deterministic complexity, so no delta shows up, or we have something with the usual rate in epsilon. But how does the delta, the logarithm of 1 over delta, come into play? There's some power 1 over q divided by q minus 1 times r over d plus 1. And what we can see here is the higher the smoothness r, the smaller this exponent gets. So the fewer samples we need. But the higher the smoothness, the smaller the cost we need to the smaller is the cost we need to take to achieve that additional accuracy. No, just let me tell me once more. The higher the smoothness, the less does it cost to increase the confidence level. So with smoothness, we can exploit this also for this probabilistic error criterion. Sometimes, I forgot one thing. What does it mean, sufficient smoothness? Sufficient smoothness means that the Sobolev spaces are embedded in the space of continuous functions, so that they can use function values of a deterministic method. Otherwise, it wouldn't work, and we would need random methods for approximation, mating the function, and this will be tricky. I don't think that this works in that way. So this is why we have this additional assumption on the smoothness for that this method works, so that deterministic approximation works. And so we had an algorithm where there was a median of means inside, so some nonlinear feature, but in some settings it's also there are methods which are linear and also have the correct order, the optimal confidence properties. And this is stratified sampling. The idea is to split the domain into subcubes and use one random function value from each subcube. So here you have divided into 3 to the power of 2 subcubes and take a random function value from each of them. And of course, because of the smoothness, there's a little variation within each cube, and this makes the Monte Carlo method more efficient. And we average those sample values, and this gives us the stratified sampling method. Using Hofding's inequality, and concentration inequality, we can prove optimal rates in terms of those epsilon delta error criterion for several classes. For example, for Hilder classes, Hölder continuous functions with arbitrary Hölder exponent, or for Sobolev classes with smoothness 1 and integrability big enough so that the functions are still continuous and big enough that they are bigger than 2, so not small integrability. In some cases, we do not know. If you have the one-dimensional case, it could also be small integrability between 1 and 2, and there we don't know the exact rate, and we don't know whether this method achieves it or not. Might be an interesting problem to think about how we could deal with low integrability here. Probably we need to somehow treat outliers of the function, because in low integrability there might be peaks of the function, and if you accidentally hit a peak, then this could destroy your confidence of the method. It could happen too frequent that you have an outlier of your function. Yeah, the difference is here in the part how well can this be improved. Can the integration improved by Monte Carlo? In the lower bound we have something like this, which depends on p. If p approaches 1, then this exponent approaches 0, so the closer we get to integrability 1, the less Monte Carlo will help. This is what you can see in the lower bound. And in the upper bound, there's an error here, I think. There's an error here, it's wrong. It should be only the square root over logarithm of delta to the minus 1, but n should be with the weak power. Sorry, I need to correct this. There's a gap, I want to say. So these are isotropic spaces, but we have here a conference on hyperbolic cross approximation. So what about mixed smoothness spaces? Here we take derivatives with the absolute degree of the derivative bounded by R. So we have a lot more derivatives which play into that norm of that mixed space. But we have a similar lower bound with the same proof technique. It's only n to the power minus R, not R divided by D, but this remains the same. And what do we have in those cases? If you take probability amplification of an algorithm Mario Ullrich has analyzed very optimally, it has the correct order in the standard Monte Carlo error. Then we will find an upper bound which has the expected order of convergence in n, but the power of that logarithmic term, depending on delta, is not optimal. It's too big. And this bound only holds for large n. Should be larger than this logarithm of 1 over delta. We also had contravariates, or separation of the main part. But we know that we have a different rate of approximation for mixed smoothness spaces with additional logarithmic terms in n. And this somewhat destroys here the order in n a little bit, but we have the correct order of the logarithmic term on delta. So delta goes in the right order. Also, this only holds for n larger than logarithm of delta minus 1. And if we have fewer function values which we may use, then we have deterministic quadrature. Then it's close to the lower bounds, but disturbed by those logarithmic terms. For the last two results, so we need a deterministic approximation and also deterministic quadrature. You can find those results in a paper by Zung, Temlyakov, Ullrich from last year. So this is a deterministic rate, but this is not what we have in the lower bounds for the randomized setting. There are some open problems. And I want to explain to you that the method of where we have taken, like from Ullrich has studied, there we have the correct order in n, but we needed to amplify this to have at least somehow good confidence properties, even if it's not optimal, as we suspect. Still, this method has to be amplified. Without amplification, it doesn't have good confidence properties. When I explain this, the algorithm was introduced by David Krieg and Erich Novak, and Mario Ullrich. He has improved the analysis of the algorithm, and it was a randomized Frolov quadrature. So you have some Frolov quadrature, some Frolov grid, but introduce some randomness, some random shift, and some random dilation. Could look like this. And you have some average of the points evaluated here within the domain of the function. It's restricted to functions with zero boundary conditions, but with some variable transform you can put any function into that shape. So results also transfer to functions without zero boundary conditions. This method achieves the optimal rates for the standard Monte Carlo error, but the confidence properties are not optimal. And I want to explain this with a one-dimensional example. I've considered, we have considered a certain rate of delta should be like 1 over n. So depending on the number of function values we take, so we look at a certain angle through the complexity domain, so parameter domain n and delta, and study that randomized Frolov method for a Hilbert space setting. It was easy to study, and we see that there is a gap. I don't want to go into the details how this can be seen. We achieve with this method, we achieve cannot do better than the deterministic rate, but for this delta, it should still be better if we have the if we consider the lower bound we obtain for the probabilistic Monte Carlo error criterion, where we have only the logarithm, the square root of the logarithm of delta, 1 over delta. And how do we show this? The Fooling functions, they consist of bumps with gaps. And this randomized Frolov quadrature could happen to compute only function values within the gaps. So it only sees 0, 0, 0, and the output will be 0. So the error will be the integral of f. Could be like this. And the probability that with this random shift and random dilation, that we only hit the gaps, this probability is unluckily too high. So this is why we don't get the optimal confidence properties. What else do I want to say about this? Should also work in the higher dimensional case, but I think this can be understood in this case. This is a major problem of that method. It's, but I must say I expected it like this. If you look at concentration inequalities, they usually apply when the number of random parameters goes to infinity, or grows. The number of random parameters grows. But here you only have random dilation, where you have d parameters which are random, and you have a random shift, which are d parameters which are random. So the number of random parameters for this method is fixed for the dimension. It's not growing with the number of function values we take. So this is why no concentration inequalities apply. We should expect that for almost every new function value there should be some randomness included, and then probably we can include we can work with concentration inequalities. This is what happened for stratified sampling, where you had one random function value out of each box. Every function value had some randomness inside, and then a concentration inequality applied. This is not the case for this method. So how could we work with this? How could we study this in the future? And mixed smoothness spaces, because of the additional logarithmic terms in the approximation. Probably we need alternative approaches for a good Monte Carlo quadrature rules. So what about confidence properties for jittered Frolov? So that each point of a Frolov rule is jittered. Might include more randomness, and maybe then we can apply concentration inequalities or maybe other ways of spreading points randomly inside the domain. Could be negatively dependent point sets. I don't know whether this notion is known. I think it's there are some papers by Michael and Martin where they have used this term, so that all points are random. They do not lie too close together. There's some structure inside that, so that we can exploit the smoothness of the function with every function value. But this has to be studied. Or for low integrability, probably we may have a fancy sampling scheme, fancy randomized sampling scheme, but we need to identify outliers, so peaks which we have accidentally hit, and remove those function values. Don't let them have such a big influence on the output of the algorithm. So this would then be nonlinear features introduced to the algorithm, probably necessary for low integrability. And independently of interest would be also confidence properties for LQ approximation, if those Sobolev spaces are, or also mixed Sobolev spaces, are not consist of discontinuous functions. There's a lot to study, I think, is left. And with this I have some references, but at this point I hope that many interesting discussions will start, and I thank for the interest and the attention.
Thank you. Thank you very much. So, time for questions or remarks. Yes, Mike?
I found your here observations that you need a little bit more randomness to use these concentration of measure results. Interesting, because Marcin and I, we also studied some kind of lattices, right? And if you just randomize them, and if you just randomly shift them, and if you just choose the generators, that should be rank 1 lattices, if you choose the generator randomly, then they don't have negative dependence property, which here immediately would give you some here concentration of measure results. But if you jitter around a small volume, like let's say if you have n points, you look at a volume of 1 over n to the power d, which is really small, right? So because you just have n points, and if you jitter there, then suddenly you get the property. So the jittering takes only place in a very small volume. This already gives you from no negative dependences, shifts it into the regime of negative dependence, and then you can apply these kind of concentration of measure results.
Yeah, that will be interesting. I mean, we have lower bounds and they are to match. This is the gold standard.
Thank you. Mario?
To your slide 10, so of course it was everything afterwards, but would you show us slide 10 again?
You know.
Okay. So probably that's usually Hendrik's question, but what about the dimension for the first part? Because now the order is not dependent on n, so one could at least try to do something there.
Yeah, dimension dependence is missing on the slide number 13. This is also a good open problem. I mean, we were
you know nothing, so
we have nothing about this. It was a starter, this paper, because we realized that well, in statistics it's common to study this criterion for a method. Yeah? Like, what is the error with which probability can we guarantee which error? In IBC, no one has done this, so we said, okay, make a starter. We have some lower bounds, we have some matching upper bounds in certain cases, and show what could happen And this would be a good direction of research. Tractability with Monte Carlo methods and well, I mean, actually, no. If you do Lebesgue spaces, if you have Lebesgue spaces and want to try to integrate functions from those spaces, there you have this is independent of the dimension, and we have with Monte Carlo methods. So actually, in that case, if you go back to that case, then you can forget about the dimension dependence. So there won't be a curse or something like that. This is what I can say.
Sure. I mean, do you get something like this with the optimal order of convergence? This was
yeah, so pre-asymptotics and so on, no, we don't have.
Okay, some other questions or comments? If not, let us thank Mr.
Thank you.